12:30, we'll meet outside here, and we'll go together to Galilei's house.
You know, she's offering welcome.
Yes, for the visit and for the welcome party.
What's that?
Yeah.
Okay, great. So, well, let's continue. Hopefully things will be mostly somewhat more down to earth from now on. So, let me just remind you this. So last time, we sketched a construction of, so K is a ring. We sketched a construction of something we call K-mod. It was something called a stable infinity category. So stable, let me remind you, meant that fiber sequences were the same as co-fiber sequences. So in other words, if A to B to C is a fiber sequence, in other words, A is the fiber of the map from B to C, then C is the co-fiber of the map from A to B. There is also inside this the ordinary category. Okay. So now let's, so this map, again, sent a module M to its projective resolution. So that was the functor. So I want to try to compare these two categories a little bit and give an example of one instance, one way in which this category is an improvement over this one. So a lot of times there are things that look like they should be more or less the same, but which are not the same at the level of Mendelian categories, but which become the same at the level of derived categories. So we can consider, so in general we can consider quiver representations. So for those of you that don't know, a quiver is just a directed graph. And a quiver representation, well, typically you put a vector space at every node, and you provide a linear map at every morphism, for every arrow. So one way of saying that is, well, typically people take the path algebra of the quiver, but slight variant of this is we can interpret the quiver itself as a category, because the objects are the nodes of the quiver, and the arrows are and the morphisms are generated by the arrows. So a representation is just a functor from Q to some category, so K mod. So I want to consider a particular example, a pretty simple example. Let's call it 0, 1, 2 to n. So I think this is called the source quiver. So there's n plus one nodes, and one of them maps to the rest. So what is a representation of such a thing? So representation. Let's first do this in the non-derived world. Well, it's a map. So to each Galilei associated vector space, it's just a diagram like this. V0 mapping to the direct sum from I1 to n, Vi. So Vi is what we associate the ith node. On the other hand, we can consider another quiver where we reverse the arrows. So this is like a source. I think this is called a sink. And this is the same kind of thing, except now we have a map from the sum of Wi's, 1 and to W0. So now there's a relation between these two. There's a way of going from one to the other. So in particular, suppose F, suppose F is injective, well, then we can consider the map to the quotient. And this produces an element like this. We can just call this W0. Get a representation of this quiver. Similarly, here, if this map is surjective, we can take the kernel of this map and we get a representation of this quiver. So this looks like this kind of procedure should give an equivalence between this quiver and this one. But of course it doesn't, because it only gives an isomorphism on the subcategory, where this map is injective, or this map is surjective. So almost an equivalence. So passing to the derived world is something that fixes this. If you see this as a problem, at least, it's something that fixes this problem. So representations in K-mod, well, they look the same way. You have V0 mapping to the direct sum of VI. But now you can take W0 now to be the cofiber. And again, because we said that cofiber sequences were the same as fiber sequences, now V0 is the fiber of this map. So the upshot is there's an equivalence of infinity categories. Let's call this Q0 and Q1 maybe, between representations Q0 and representations of Q1. So somehow, instead of kernels and co-kernels, in the derived world you have fibers and cofibers, and they tend to remember more information about your map. So somehow, even if this map were not injective, this cofiber remembers something about the kernel of this map as well. Yeah?
Your implies there exists nothing of infinity diagrams.
Oh. Sorry, I'll put this. So hopefully this provides some. So I should say I gave an abstract definition of what a cofiber sequence is or what a fiber sequence is, but I also told you a very concrete interpretation of it, which is that you can check that something is a cofiber sequence or a fiber sequence equivalently by seeing that you have a long exact sequence on homology groups. So in particular, if you had a candidate for if you wanted to explicitly compute this, if you had a candidate cofiber, it's pretty easy to check in practice once you have a candidate that you have the right one. So in particular, as an exercise, I suggest working out if you have a map of chain complexes what the cofiber is. Once you know what you're doing, it's not a very difficult exercise. All right. So hopefully this gives a little bit more motivation to having to derive things. So now I want to start moving towards talking about geometry. But before we do that, suppose we have, I'm going to start calling K something else now, I think. Suppose we have a map of rings. So then we obtain functors. We have F lower star from B mod to A mod, and F upper star from A mod to B mod. So this one is kind of tautological. So if you have a B module, you can regard it, if you have a complex of B modules, you can regard it as a complex of A modules, just by forgetting. Here, the operation is tensoring. conflicted whether to decorate this with a symbol L, but so I will not. But I will verbally point out that this is the derived tensor product. The reason that I'm not decorating this with a symbol L, as people often do, is because in this context, no other thing makes sense. If you accept these as infinity categories, this notation is not completely unambiguous.
Can I ask you your example before you remove
Yeah.
it? So the category rep, the usual one in K-mod parts for Q naught
Are not
is inside of what you're calling now rep Q naught.
Yeah.
And now where does it map with this infinity function?
Well, it doesn't. So if you take this guy and map it here, well, in general, you land outside. And the way you know that you land outside is because if you have a kernel of this map and you take the cofiber, this will be a two-term. This will be a complex which has cohomologies in 2 degrees, as opposed to just a vector space. So in 1 degree it will be the co-kernel, the cohomology, and then the other degree will be the kernel.
Yeah, you're explaining me that it lands outside of the hard one, but
Yeah.
I wonder what is this category? I mean, is it a natural category inside of rep Q1?
Yeah, it's one where well, one property that it will have is that all these guys, all the VIs, live in the heart. And the double.
So they are cokernel. You're describing what cokernels are somehow.
Yeah, and this guy lives in 2 chronological degrees, and there's an extra condition to make sure that the kernel lives in 1 degree. So, I mean, there's not a particularly nice description, but you can pretty explicitly do
Is
it.
there something like the orientation of the computer gives you some destructure on the representation category?
Yes, so I don't think, well, I don't know what an orientation of a quiver is. I mean, you cannot take a graph and ask to make it directed,
Yeah.
but in general, that won't be an equivalence. You know, in general, the category, even the derived category might depend on the, because, you know, if you had some other thing here, it was just something special about this.
Can you invert one arrow?
I'm sorry?
If you invert just one arrow, will it also be equivalent?
Oh, if I invert just one arrow, no, I don't think so. I mean, you might want to take dual or something like that, but if these are not finite dimensional vector spaces, then there's no way, yeah, so. Yeah, so I'm pretty sure those won't be equivalent if you just invert one arrow. The important thing is reverse all of them.
And if you have a more complicated cleaver, reverse all arrows, do you get infinite equivalence? Or does it
I
work
also,
for this
yeah.
other example?
I don't have a counterexample, but I don't think so. So we have these natural functors for restriction and induction, or push forward and pull back. So by the way, the reason lower star is usually a functor that goes forward and lower functors go forward and upward go backward. The reason for this notation is that I'm secretly thinking of these as geometric objects, which is a contravariant operation. Anyway. All right, so let's talk about, let's get back to geometry now, having said all of this. Geometry. So suppose X is an algebraic variety. Okay. Field characteristic 0. None of these assumptions will be necessary, but for psychological reasons, eliminate them. And algebraically closed. So you might as well assume it's C.
Call it C.
So you can perfectly well think it's C. You will lose absolutely nothing by doing that, but I like calling C K for some reason. So we want to define the derived category. So I'm taking the word variety, by the way, to mean smooth as well. I think that's sometimes what people do. Category of quasi-coherent sheets. So there are several approaches to this. Oh, actually, before I get to that, this is what we're going to do. But first, I'd like to spend a minute dwelling on what an algebraic variety is exactly. So the reason I didn't want K to be C is because I don't want to allow myself to consider the analytic topology. I think that's the reason. I don't like the idea of putting C there. But so what is an algebraic variety anyway? So there are kind of two approaches. So the more classical approach is it's like a manifold and glued out of local pieces. I mean, you always want to say that, but in particular it's a topological space with, I'll say, a sheaf of rings. So, i.e., a notion. So there's a notion of an algebraic function. So for each open in this topological space, I sort of specify what functions on it are algebraic functions. So for those of you not familiar with the algebraic point of view on algebraic geometry, as opposed to the complex analytic point of view, I'd like to point out that here, when I say topological space, well, if I was working in the complex analytic setting, I would mean really, the kind of topological space you're used to, Hausdorff, all these good things. Usual analytic topology, and as long as I replace algebraic by holomorphic. But if I wanted to work in algebra, the substitute for that is the Zariski topology on the space. So the Zariski topology is a little bit strange. It's not Hausdorff or anything like that, but it's still worthwhile to consider. Well, it's very easy to say the opens are complements of algebraic subvarieties. This forms a topology. It's a very coarse topology, but nevertheless, one will make effective use of. But really, you don't lose much by thinking of the same concept in the analytic category. But the second approach is this functor of points approach. So, for those of you who are used to kind of the analytic way of thinking about things, this will be very foreign probably, but algebraically, well, in general, it's a very fruitful approach to things. So the idea is this, is that an algebraic variety is the zero set of polynomial equations. Well, but what does zero set mean? So you have some polynomial equation. You have some polynomials, and you want to solve for x. You want to find which x you could plug in so that the equations vanish. Well, that's not sufficient if you think about it, because you have to first say where x is allowed to live. For instance, you get very different answers if you try to solve some polynomial equations over rational numbers or over complex numbers. So instead of fixing this choice of where your solutions are allowed to live, you can vary this choice over all possible rings, and so, as long as you remember the compatibility. So solutions define a functor from rings to sets. So given a ring, you can associate to it a set of the solutions of your equation. And if you have a map of rings, well, if you have a solution over one of them, then the image of that will also be a solution of your polynomial equation. So any algebraic variety we can think of as a functor from rings to sets. And in fact, this retains all the information. Oh yeah, rings. So that's another very worthwhile point of view. The equivalence of these points of view is something called Yoneda lemma in category theory, which is well, it's sort of like Shor's lemma in representation theory, which is its proof is completely trivial, but it has very far-reaching implications. So anyhow, so just to give you an idea of how this works, if you're unfamiliar with it, I'll give you two examples. So the first example is AN, the affine space. Well, so as I assume everybody knows what affine space is from this point of view, but as a functor of points, what is it? Well, it sends a ring R to where? Well, it's to just R to the n. In general, maps from anything into AN is just the same as the data of n global functions. So global functions on the geometric object corresponding to R is just R by definition. So I guess another example is that, well, there's something called spec R, which is a little difficult to build as a topological space with a sheaf of rings. I was looking at primes and whatnot, but in terms of the functor points, it has a very simple description of maybe S. This is the same as maps from R to S. So, all right. And the third example I wanted to give, the only non-trivial example that I will give is Pn. So, maps. So, to describe it as a functor of points, well, it's enough to say, I'll take a little bit something more general than rings. I'll say what it is to map any variety into projective space. So this is the same thing as a line bundle on X with a surjection of n plus 1 copies of the struct so O. I haven't defined it, but I hope it's standard enough. It's the functions on X. It's the sheaf of functions on X. A surjection from this to L. To some appropriate notion of equivalence. So, well, I don't want to go into the details of this, but if you're not familiar with this, I strongly recommend working this out. It's a very important example. So okay, so that's what varieties are. Now sheaves. Now quasi-coherent sheaves. So there are a few approaches. So the first approach, let's say on X. So the first approach is we can consider all sheaves of OX modules. This is sort of the classical approach. I'll mention it, but I won't use it because I think it's not a very useful point of view, but maybe it's the one that's most intuitive. Is consider OX mod. So this is the category of sheaves of OX modules. So this thing is constructed in exactly the same way, or very close to the same way as we constructed our mod. Here, a better idea is instead of projective resolutions to take injective resolutions. Those will always exist. And then define the then define quasi-coherent sheaves as the subcategory of OX mod. So, well, subcategory just means we pick out a class of objects and the morphisms between are the same as the morphisms in the original category. So F is in this quasi-coherent category if HI of F is in the, well, is quasi-coherent as just a non-derived sheaf of OX modules. So do people know what just a quasi-coherent module over OX is? So let me remind you. I don't know, M maybe. So this is also a subcategory of OX mod part. So this means the following, that suppose I have a U which is affine. So general variety has an open cover by affine schemes. So the notation for affine is the spectrum, then the restriction of M to U, well, is isomorphic to M of U tilde. So this is the sheaf on spec A associated to the module, the A module. Of U. So the way sheaves of OX modules work in general is that if you have an open, you evaluate on it. You can evaluate OX on that, that's some ring, and then you evaluate your module on that. Whatever that is, that's going to be a module for whatever the value of OX on that is. So M of U is in particular an A module. And given an A module, there's a canonical procedure which constructs a sheaf on spec A, and we're required that these be the same. Anyway, I don't think I can say much more than that without really having this take us very far afield. But if this doesn't make sense to you, don't worry. I'm about to give a different definition, which doesn't involve futzing around with this bigger category. That's sort of the main disadvantage of this kind of definition, is that we're first forced to define a larger category and to build the category we want as a subcategory. So a second definition is the following. Take an open cover UI of X. So what kind of thing does that give us? So we have a map from the disjoint union of the UIs to X, that each of these is open and this map is surjective. And we can take the twofold intersections. So this gives us a UI intersect UJ, and then we can take the threefold intersections. JK, UIJK, and so on. So in a way, this gives us sort of simplicial resolution of X, and we can apply the quasi-coherent sheaves on X. You can define as as the inverse limit of quasi-coherent sheaves on these, you know, this diagram. I'm sorry. Whoops. One. Okay. So anyway, because we know what the value of quasi-coherent, if we were to know what the value of quasi-coherent sheaves on all of these guys were, and what restriction maps these maps induce, well, we can just take the limit. So this looks very abstract. Let me try to unravel it a little bit. So this only, well, let me say this. Let me maybe state as a theorem from this definition that there's an isomorphism like this. So this might not look so helpful if our goal is to define, because we need to define these things because we need to know what each of these categories are. Also, there's this funny inverse limit operation, which maybe is completely obscure what this means. So let me spell out these things. So on U is equal to step A, the key point is that quasi-coherent sheaves is isomorphic to A mod. So now we have a different definition of what this means, which is the same. And this is with respect to the pullback operation. So 2 is saying that specifying a quasi-coherent sheaf, on X is the same as specifying a compatible collection of, I guess, modules for an open cover. In other words, so let me, you know, this kind of limit thing might look a little scary. So let me give an example where suppose X is a union of two affines. So let's say that X is equal to P1. Then this is the union of A1 over A1 over GM, which is A1 minus 0. So well, the point is that to specify a sheaf on X, you specify a module for this polynomial ring in one variable, a module for this polynomial ring in one variable, and an isomorphism of their restrictions here, which is the sort of thing hopefully you're all used to in doing check cosines. So this is exactly specifying a sheaf using its gluing data. So I won't spell it out, but compatibility here is that this coordinate is the inverse of this coordinate. So anyhow, so you can take this as another definition. It's just that pick an open cover, and then we know what quasi-coherent sheaves on each of the pieces of the cover are. They're just modules for the algebra, and then combine them together in this coherent way. That definition is also not entirely satisfactory because it involves the choice of open cover. In particular, if I gave you that as a definition, you could very reasonably ask the question, well, suppose I chose a different cover. Would I get a different answer? So there's a more universal thing to do, which I'll just give the definition and not say much more about. So this really takes this functor of points approach very seriously, is to define quasi-coherent sheaves on X. By definition, it's going to be the inverse limit in this higher categorical sense of spec A mapping to X. But this is another name for X of A. Of A modules. So, well, maybe it's not a priori clear that this definition is equivalent to this one, but at least it's absolutely apparent that it is completely canonically associated to X.
It's also better suited to because you have to assume the intersection of a file is a file, right?
Well, I could have fixed that. So first of all, I assumed variety. So that's fine. Variety isn't necessarily separated. I could have taken a hypercopy. But yes, it is better in that way also. So anyway, so that's the definition. And the way you work with it is really by unraveling the tool. So you choose. If you wanted to write down a sheet, typically what you would do is you would write down a cover and do this. Sometimes you specify it in this way. Well, we'll see. All right. Okay. So that's the definition of this abstract category. So how does one really work with such things? Yeah. So if you're not used to sheaves in general, let me give you some examples of objects in this category. Really, most of these examples will be objects in the heart of this category. But nevertheless, it's worth to keep these in mind. And in fact, everything can be sort of built in some formal way out of these things. Examples. So suppose we have a divisor. I hope everybody knows what a divisor is. It's here I just mean it's a, let's say, smooth codimension 1 subvariety. And we can define O of D. This lives inside O. So X. This is functions which vanish in D. So, by the way, it's a geometric statement. The reason I wanted this to be a codimension 1 is otherwise this would be pretty degenerate. A function that has a 0 always has a 0 in some codimension 1 subvariety. Okay, so you can define this. So there's another thing of minus d, which is functions maybe a little bit more interesting with a pole of order at most 1. And I screwed this up, didn't I? It's not a good sign that nobody corrected me. Please, what's that? Anyhow, so of minus d is the notation for things that vanish. Of d is functions of poles. This is the thing that has sections to distinguish. Anyhow, so that's one thing. Let's probably include an I. You can also take formally the I lower star of pulse of d. So just push forward a structure sheaf. So there's actually an exact sequence relating these things. There's an exact sequence. From this, more or less for tautological reasons, because functions on D are the quotient of functions which vanish. About those which vanish at D. Yeah. Great. So that's one set of examples. Playing with divisors is really a rich theory.
I'm a bit confused. I'm sorry to be very anal, but what does exact sequence mean?
No, so this,
Are you in heart?
so I guess I should write it like this, but this actually is all in the heart. So this is a fiber sequence. And this comes from an exact sequence. In the heart. So we saw last time that exact sequences in the heart give you fiber sequences in the derived category. Okay. So another set of examples is if V is a vector bundle. On S, so we can define E to be the local sections, or sections of E, so the chief of sections. B. So this is a very natural thing to consider, familiar to everybody, and somehow every quasi-coherent sheaf on X is built out of push-forwards of vector bundles from some varieties via, the standard operations that we have, taking cones and various kinds of other colimits. So another example, which is the tangent sheaf. So this is this construction applied to the tangent bundle, if you like. And what I'll call omega 1x cotangent sheaf. So this is I guess this has another name in this context. It's called Taylor differentials. So, as a very simple description to an open affine, it assigns all the possible algebraic one-forms. That's dual to the tangent sheaf. So, well, as an example, let's consider what the tangent sheaf of projective space is. So projective, from here, we'll think of projective space as geometrically as possible, and we'll think of this as an plus 1 minus the origin, quotiented by GL. And so the claim is there's a fiber sequence, which also is really an exact sequence. So it's called the Euler sequence. It goes like this. Let's screw it up. So 0 goes to the structure sheaf of Qn. N plus 1 copies. Oh boy. I'm getting ahead of myself here, aren't I? I'll return to this in a moment. I apologize. Looks like I forgot to define something.
You write O1?
Yeah, that's a 1. All right. Tn of 1 to the n plus 1, and then Tn. Well, that's not so useful. Let me explain what O of 1 is. a hypersurface. H, and define O of 1 to be O of minus H, O of H, I'm sorry. Yeah, so this involved a choice of hypersurface, but P1 is very symmetric. So as a consequence of this, as a sheaf, this does not depend on it. So there was a fiber sequence like this. So the map to O depends on the particular choice of hypersurface, but the underlying sheaf does not.
Hyperplane.
Yeah.
Hyperplane.
Hyperplane. Thank you. Apologies. So similarly, O of n is well, O of 1. That's our n, or O of minus 1 tensor minus n, depending on whether n is positive or negative. I didn't tell you how to take negative powers, but here's such a thing. Well, one claim is that, actually, let's say exercise, is that sections, so global sections, of O of n are the same as it's homogeneous, degree n, and homogeneous polynomials in, oh boy.
Should not take n.
So m, it's a degree m homogeneous polynomials in n plus 1 variables. So I won't explain the details of this, but it comes from thinking of Pn in this way. So anyhow. So now at least this makes sense, and so does this. So let me, so this is called the Euler sequence. So let me tell you what Euler has to do with this and why you have such a sequence. It has a very beautiful geometric explanation. Is that if we choose, so let's say Pn is the projective space of K to the n plus 1. So we have to say, let's choose some coordinates for the underlying vector space. And then, so if Vi are linear functions on V, the vector field. So we can consider the vector field Vi a d dxi. So the xi are, remember, the coordinates on V. So we need n linear functions. So this vector field descends. So this is a vector field a priori on a n plus 1 minus 0. So this descends the vector field on Pn. And this guy, so n plus 1 linear functions on this guy is exactly what sections of this are. So this gives this map. So this defines the map. So O of 1 plus 1 is Pn. So this is the, that's the map, and the kernel is given by the Euler operator. So this is normal of xi d by dxi. the kernel of this map. This is the operator Euler studied. It's the infinitesimal operator of rotations, and it has the property that if f is a homogeneous function, then the Euler operator just multiplies it by the degree. It's a very easy exercise to check. Anyway, so this is a description of the tangent space of Pn. So these are both reasonably accessible, and now one can understand what they. So any questions about that?
This is the classical description, if I understood correctly.
Yes, absolutely.
As opposed to this spec of A, this inverse limit of spec of A.
That's right. That's right. But, well, I mean, all of these are kind of equivalent. So both points of view are very useful. I mean, to describe the tangent space of projective space, well, I guess one could define it in terms of the functor points that I get, but this is probably much easier. So
why is it better to use functor points?
So functor points is better for. There are some formal manipulations one wants to do, and there are some geometric arguments one wants to do. So the functor points tends to be much better behaved for formal manipulations, but for geometric arguments, the intuition coming from the analytic topology tends to be much more helpful, or at least that seems to be.
You had chosen to describe omega 1 is much easier with the functor point, for example.
Yeah. Yeah. I mean, part of the reason I explained it in this way is I wanted to relate it to the classical description and explain that it really does give something in this formalism. So, I don't know. These are they're equivalent, and one is different aspects of various questions. You might want to switch to one viewpoint or another, but it's really worthwhile to have both viewpoints in mind. Okay. So in the last few minutes, I wanted to calculate an example of a derived category. So just to show you that, I mean, so far nothing was happening in the derived category. All of these statements could have been said at the level of the abelian category. So so let's consider. So let's study the derived category of P1. So, well, where to begin? So there's a beautiful idea of balancing. Well, the idea goes like this. Suppose we have a sheaf which lives not on P1, but on the product of P1 with itself. So we have this silly diagram. So the first projection and the second projection, we can consider the functor. It's going to go from quasi-coherent sheaves on P1 to quasi-coherent sheaves on P1. It's going to take, let's call it M here. We're going to do the following. We're going to go back. Now, oh, by the way, I forgot to mention that on general quasi-coherent sheaves, we also have the pullback and push-forward functors, and they're just deduced from the ones for rings. So, for instance, one answer to your question is merely the existence of these functors is an easy consequence of the definition in terms of functor points, and sometimes it's a little difficult to establish them otherwise. Then we can take this tensor of Y by F. well, I guess that's even more believable, that there's a tensor product operation, which on affines is just tensor product of modules. So it's tensor over OX. And we can push forward with respect to the second guy. So let me call such a thing an integral transform. So the way you should think of it, so it's purely by analogy with the usual integral transform, where you think f as giving the kernel. So usually if you think about integral transforms, you have some kernel which is a function of two variables, and you integrate against it as a function of one variable. So pulling back is like regarding a function of one variable as a function of two variables, but by just forgetting one of the variables. And pushing forward is an operation analogous to integration. So this kind of pulling back, tensoring and pushing forward is some higher version of, or analogous to taking an integral transform. So we can consider such a functor. And the main idea here is that you can study transformations from this category of quasi-coherent sheaves of one thing to another by studying integral kernels. This is a powerful idea in analysis, and it's an equally powerful idea in geometry. Here, in studying quasi-coherent sheaves. So Galensson's idea was to pick a particularly nice f. So maybe we'll talk about it next time, that sheaves on here actually are tell you everything there is to know about functors between these categories. But even without that, we can pick a particularly nice f and try to understand it. So so the observation oh yeah, let me give this functor a name. Let's call this phi sub f. Or if we take the diagonal, just the structure sheaf of the diagonal, then this corresponding functor is just the identity. So I'll leave that as an exercise to check. But now, there is a resolution. There is a fiber sequence delta going to O U1 squared into OP1. So this is the fiber sequence I explained to you before. And an exercise is to check that O of delta is actually equivalent. It splits up as a
It's O of minus delta?
what's that?
Is it O of minus delta?
Oh, no, I think it's, oh, yes, thank you. Never keep the signs straight. But anyway, so that it splits up into two pieces. So if you have a product of things, you can take there's an operation of external product of sheaves. It's the simplest thing. It's just on a, the fiber is just a product from one thing and a product. There's a basis for the topology consisting of a neighborhood in one and a neighborhood in the other, and evaluated on those is just the tensor product of those things. So this is what I mean by this kind of thing. Sorry, that's a little quick. But anyway, so it's an exercise is to identify this sheaf. It's not very difficult. It's actually related to the Euler sequence for P1. But now let's use the fact that all these functors preserve cofiber sequences. So instead of taking this guy, we can take the cofiber of this guy and this guy. So the upshot is that E sub f of m, this is equal to well, so let's do it. So first we take pi 1 upper star of m. Let's just do that. And we well, I can just say what it ends up being. Tensor omega 1 minus 1 box tensor over 1 co-fiber.
So what's your F now?
What's that? F is this thing. This is F. So it's just going to be the co-fiber by this guy X. And then lower star. Well, I'll skip the co-fiber. Mapping to pi to lower star of one box tensor pi 1 upper star of m. So this is what it's going to be. And the point is, for the kinds of sheaves that are the external product of things, it's extremely easy to produce, to calculate the push forward under the projection. Same way that if you have a product of functions and you want to integrate along one of the variables, well, you can take the other one out and just multiply it by the integral of the other one. So there's exactly the same formula here. So this is the same as let's see, O of 1 tensor over K, not as a vector space with
I'm sorry, how can you have a box product with pi 1 upper star?
oh, I'm sorry. Oops. Thank you.
No,
And here too. Alternatively, I can replace that. Well, anyway, that's that. I'm sorry. Trying to not run over too much here. Is that okay? Tensor. Wow. So P lower star. Tensor omega 1 minus 1. Mapping to O to 1 tensor over K. So P lower star of M. So P is just the map from P1 to point. So this is what, well, another name for this is R gamma. So this is the global section. So this is the push forward to the point. So what's the point of all of this? The point of all of this is that I can build any, I give a canonical presentation of any sheaf as a cone of O of 1 tensor some vector space. So some co-limit of O of 1 with just O. So the whole category. So once you know about O of 1 and O, you know about the whole category. Because you can build, by a finite procedure, you can build any sheaf, and here's the procedure, out of O of 1 and O. So the upshot I will say P1 is, I'll put in quotes because I don't want to define this word, is generated by O and O of 1. So I don't want to leave you hanging with a vague description. So whatever generated means, it means that if we understand everything about these objects, we can describe the category. So the thing to understand about these objects is Hahm's between them. And the Hahm's between them are as follows. So we know that Hahm from O to O is just K. There are no higher ones, so this is all in degree 0. Hahm from O of -1 to O is also K, O squared. So this is the same as from O of 1. So this, remember, is a degree 1 is linear functions on a two-dimensional vector space, so that's k squared. So O to O of minus 1, this is 0. From O of minus 1 to O of minus 1. This is going to be also k, because both of these are given by tensoring by something. So line bundle. So really the upshot, and I recommend understanding this statement, is really the upshot is that the quasi-coherent sheets on P1 are equivalent to representations of the quiver given by two nodes and two arrows in this direction. So let me label this O of minus 1, and this is O. So it's exactly, well, you see that, at least you see that the things in the representation satisfy this. Okay, I will stop here. Sorry, that was a little bit rushed. Yeah.
About your definition of quasi-coherent sheets.
Yeah.
It's going to be very naive on my part.
Okay.
But my notion of quasi-coherent is a notion of boundlessness. It's something that I want to work with large things, but I don't want them to be very, very large.
Oh no, there's no boundedness in one.
Well,
so like if you think about the derived categories, this gives the unbounded derived
but I want to be presented. So that's I want to be locally presented, and this is my notion of usual quasi-coherence.
Oh wait, sorry. As a category locally presented?
So it's my notion of instead of arbitrary sheets of all modules,
yes.
I can work with quasi-coherent sheets. And this notion originally was a notion of, well, I don't want to work with arbitrary guys, I want something that is locally presented.
Oh, locally finitely presented?
No, this would be coherent.
Okay.
The notion of quasi-coherence.
I don't know what you mean by locally presented. Those words have multiple meanings, and I don't know which one you're referring to.
The local is a quotient of a free sheet, or a free module overall. So this is the usual, this was the EGA definition, say, of quasi-coherence. But it doesn't matter, this is not connected to my question, this was just a motivated question. My question is,
but that would be true here, automatically.
Yeah, I understand, but the thing is how to write this from your definition. Your definition have a limit,
yeah,
right, of A modules, which I understand that this is quasi-coherent on each appointees,
yes,
over intersections.
yes,
And the
so
thing is that now your maps are in the derived sense.
yes,
So this limit, this is my not understanding how large things get nasty, right? You're taking binary products in the derived sense,
yes,
and you're taking a projective limit over this.
yeah.
And I wonder, how large this gets.
Oh, so this, I mean, whenever
Your intersections are just not right or are derived in this picture? I assume your intersections were not derived objects.
No.
Were not derived.
No.
But if I have to take this definition in the derived setting,
No, it'll be the same. It'll be the same. Because if you intersect, there's only one way to intersect open sets. There's no derived way to intersect open sets. And
Okay,
pullback
so
is an exact functor because it's a flat map. An open map is in particular flat, and so pullback is not a derived.
okay, but so this
There's nothing to derive. So that's not an issue.
But this is assuming that your A's are actual rings. So the spec A's that you're taking, even if they were derived, then you wouldn't have any problem.
So you wanted to replace rings by derived rings in the
Right.
definition. So if your original thing was a variety, like an ordinary variety, then by a very simple yoga, you'll see that all rings form a final system in derived rings, and so the answers will agree.
Go with the same one.
Yeah, so from a direct point of view, that would be a slightly better thing to consider, although I didn't want to talk about derived rings, at least not yet, but it doesn't matter here, it gives the same answer.
So if there are no more questions.